Yeah, I used to be a great man who sat under a tree. A Newton. Oh, we're looking at a solenoid derivation right now. Now, what is a solenoid? Well, take a wire with a current running through it, and instead of having it become a straight wire or even just a single loop, imagine that you have a loop on 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 loop, just like that, with a current running through it. This is a solenoid. Now, solenoids are inductors whenever we use them in circuits, but we'll talk about inductors later. For right now, let's just talk about one of the features that we see of a solenoid when we do pass a current through it. If we look at this little picture here, through the bell, what we're going to see is that as current is running through the solenoid, if we stick our thumb in the direction of that current and wrap our fingers will point in the direction of the B field, just like before. What we can also do with a solenoid is if we wrap our fingers in the direction of the current, and let's say our current here is continuing to go like this around all the sides, a right-hand rule is if we wrap our fingers in the direction of current, the direction the B field will point is the direction of our thumb. And this actually means that whenever this B field is cutting through here, like that, this is the north end of our magnet, and this is the south end of our magnet here. The B field will point north on this one, and that's because this is like inside of the magnet here, and then as we're kind of more familiar with, we'll wrap around and point back into south, okay? So the direction your thumb points after curling with the current, that is the direction of north. Now, a kind of interesting thing we see with a solenoid is that on the inside of it, the B field is actually fairly uniform. And it's actually, we're gonna call it purely uniform inside of the solenoid. It doesn't matter if you're, in the middle or if you are slightly off of the direct middle. We are gonna call the B field on the inside of the solenoid uniform. And the reason why that happens is, generally speaking, if we look directly around just these edges of the wire, these wires are going to have a B field going this way and a B field rocking this way at these wire edges, because we know the B field is going to move in circular loops. And these places here where the B field is opposing itself at the same strength, the B field is going to cancel out there. So we actually see kind of like an edging effect here, and then nothing else, which is kind of cool. What we're actually going to see because of that is while there is a slight loop kind of coming around the solenoid like this for the B field, what we actually can say, and what we're going to see in further with Ampere's law, is that this B field that I drew on the outside here, it doesn't actually really exist. Because these B fields are in opposite directions everywhere, the B fields on the outside of the solenoid are going to pretty much cancel out everywhere in existence. We're actually not going to really see that turnaround that we do here. So a solenoid is only going to have a B field on the inside, which is constant, and we typically say that the outside of a solenoid has a B field equal to 0 because of that. The diagram you see here, they kind of drew it like a permanent magnet, but we more in principle see it, experimentally, that the B field outside of a solenoid is 0 because those B fields are in opposite directions and they'll cancel out everywhere. Okay, so it's a kind of a neat thing we see at the solenoid there. Another way we can draw a solenoid is like this, where we see here all the wires going into the page up top, and they're coming out of the page on the bottom. Now, if we actually want to prove what that B field is for a solenoid, we could do this with Ampere's law, but it's going to be slightly different. Whenever we rock Ampere's law, we normally say that a closed path integral of a B field dotted through some distance vector equals mu naught times the current enclosed within it. And normally we pick nice circles to kind of loop around wire. But for our solenoid, if we picked kind of like a circle running like this, it would kind of slide in between the wires. Like if you had a piece of paper and here are the wires, it would slide between it. It wouldn't actually encompass the wires. So we can't really draw that shape. What we're actually going to draw here is we are going to draw a loop like this. And the reason we're going to draw a loop like this is going to be straightforward in a moment. When we are looking at this closed path integral, this closed path integral we have here, we have a closed square or rectangular path up top with sides, we'll call this 1, 2, 3, and 4, okay? Now, the question becomes, what of the B field is moving along that path? Because remember, the dot product we have here, B dot delta S, it is asking, of the B field that is created, which we know is only on the inside of a solenoid, of the B field that is created, how much of it is parallel or in a same direction or directly opposite for 180 of that distance vector you're looking at, of the path you're walking through? So when we look at this here, we actually see that we're going to have 4 integrals that we'd have to add over here. We'd have to add, you know, the B field along the distance length of 1 plus the B field along the length of 2 plus 3 plus 4. But we actually don't have to do that. If we think about this, path 2 here is at 90 degrees from the B field. The cosine of 90 is 0. So path 2 doesn't actually get us anything. It doesn't actually contribute to this closed path integral. Path 4, that's the same way. We don't care about path 4 because of the cosine of 90 term. If we look at path 3 out here, well, if we were to take that closed loop integral of the B field and then that path for 3, the B field out here is 0. 0 times anything is 0, so this doesn't exist out here either. The only thing we actually care about is this length in here, L. And if we're just adding up a length, then that's really similar to if I had a pumpkin roll and I chopped it up and then I put it all back together. I'm just going to get a length out of it again. So our closed path integral here is really just a B field and then ds of what is this length you have. So we're just going to get BL out of this, where L is the length of your solenoid. Now in terms of the mu naught I enclosed, we're going to keep mu naught, but I enclosed is a little weird. The current enclosed isn't just I. It's not just the current running through the wire. We have that current running through the wire over and over and over and over and over and over again. We have that current running through this loop here as many times as there are loops in the solenoid. And what we use is we use a capital N to represent the number of turns in the solenoid here. So our current enclosed is going to be mu naught times I, the current running through the solenoid, times N, which is the number of loops we have. That is the current enclosed. So kind of a weird way of thinking about that, but your solenoid could be short or it could be long, and they could have a very few number of loops or it could have many. Which means that if we wanted to find what is that constant B field, what is the uniform B field inside the solenoid, well, it would be mu naught I N over L. And I write this N over L specifically in this case because the number of loops, the number of turns in your solenoid per unit length, we can think of that as like a loop density, like it's loops per meter. So we could actually write this, and what you'll commonly see it as is mu naught I little n, where little n is a turn density. It is the number of loops or turns per distance. So that's what we're talking about there. And we see that this doesn't matter where you are inside of that solenoid. It's uniform everywhere. So that is the B field of a solenoid equation there. We also know that, hey, look, the outside of the B field, the B field on the outside has to be 0 here. One, experimentally you see that. And two, if we did run an Ampere's law through the outside, so if our Ampere's law was much bigger, if here, let's delete this real quick. If my Ampere's law was much bigger, such as something like this, where our currents enclosed here are fully 0. So that's another reason that, the B fields on the outside are going to end up being 0 as well. Not to mention that, experimentally we see that, and it's clear by the fact that B fields are vectors and they're always going to cancel each other out. So that's just what's going on there with that. But it's just another way of kind of thinking and looking about it. Okay? But that right there is the derivation of how we can think about a solenoid and what its B field is. B equals mu naught I n over L, or mu naught I little n. for a turn density, and that's a solenoid. We're going to take this same idea of building a shape and then capturing some number of turns or some number of loops in our next video when we look at how we can find the B field of a loop of loops, or what's known as a toroid. So until then, we are finished, and adios. Y'all take it easy.